Hello, my name is Sandy Oates, and today I would like to present my paper entitled A Novel Approach to Treating Ammonia and Cyanide Impacted Water with Ultraviolet Light, Field Case Study. To give you a little background on my experience, I worked in the oil and gas industry for over 25 years as an oilfield production chemist. In the latter third of my career in that industry, I found myself quite often involved with oil production projects where the water treatment plant could not meet discharge specifications for oily water. The service companies I worked for wanted to treat these issues with conventional polymer type chemicals such as flocculants, coagulants, and deoilers. At some point, I grew disenchanted with this approach and I decided to start my own company. My vision is to find solutions to these types of wastewater problems while minimizing or eliminating the use of chemicals. One of the water treatment technology advances I became really excited about was electrocoagulation. This process uses electricity rather than chemicals to destabilize oil and water emulsions and colloidal suspensions of solids. It was my first investment in equipment after I started my company. The photograph you see here is from one of the first wastewater treatment projects my company was involved in and used electrocoagulation as the primary treatment. In this case, the water was impacted with sulfides, heavy metals, hydrocarbons, and ammonia. And you can see the untreated water in the bottle on the left. It was quite dirty in appearance. In the electrocoagulation system, the water is passed through a series of oppositely charged plates. The system converts the 480 volts alternating supply current, rectifies it to direct current, and feeds it to the plates in a controlled fashion using a PLC. In this way, the electrical charges are imparted to the particles in the water, causing them to bind together, become larger, and fall out of solution. Once the water exits the electrocoagulation cells, the suspension is no longer stable, and the solids rapidly fall out of solution, as shown in the center beaker. EC exposure, followed by mechanical separation, easily handle the hydrocarbons, heavy metals, and sulfides in the water. You can see the dramatic visual improvement in water quality when you compare the treated water on the right with the original untreated water on the left. However, I knew that ammonia would be a specific problem. Going into this particular project, I knew that the electrocoagulation system alone would not completely handle the ammonia issue due to its high solubility in water. I suspected that some of the ammonia would come out of solution along with the suspended solids, and this was observed. We removed about 60% of the ammonia using the electrocoagulation effect alone, but this reduction wasn't enough to meet the client's needs. To address this, we added a number of processing steps post-EC. These included heat, aeration, and media filtration using zeolite media, which was specifically selected because of its effectiveness as a filter media in absorbing ammonia from water. As the graph shows, this was a technical success, and we were able to get down to 5 parts per million ammonia, which was well below the client's target. However, there was a price. The zeolite media spent quickly, and we found ourselves having to change out the media on a weekly basis. Removing and recharging 5 metric tons of zeolite once per week turned out to be quite a logistical challenge. It also introduced another waste stream of spent media, which was not desirable. To get ready for the next project, I went back to the literature and found that UV light could be a promising alternative for ammonia removal. So I worked with my partners at Party's Waste Management to come up with a simple laboratory study that could evaluate the effectiveness of ultraviolet light on handling ammonia. Keeping the setup as simple as possible, we used an off-the-shelf UV lamp used for swimming pool sterilization, a simple sump pump, and a 5-gallon pail for a reservoir. I placed about 15 liters in the pail. The sump pump then supplied water to the inlet of the UV housing, which was oriented vertically. The housing then flooded with water, and the outflow circulated back to the pail. With this setup, I was able to circulate continuously through the UV housing. The apparatus is shown on the left, and I've also included a picture of the lamp on the right. The lamp power is pretty low in this lab study and comes in at about 15 watts. The water we used for the lab study was pretty turbid, so we pre-treated with electrocoagulation to drop out the solids and clarify the water using a laboratory scale electrocoagulation unit. This gave me clear water to start with, which is a prerequisite for a successful UV treatment. So after running this study on ammonia impacted water, we were able to see some promising results. As the graph shows, the ammonia content was indeed reduced over a 24-hour period of recirculation. This lined up with the published information in the literature. However, I did feel that we needed an interim step before going directly to a field site, as the UV lamp power used in this lab study was really low. So my partners at Party's Waste Management came through for me again. They had a small industrial UV reactor in use at one of their treatment facilities. They were willing to take it out of service for a couple of days so I could do another set of tests with a larger volume of water and more UV power. These images show the small industrial UV reactor we used for the pilot study. First, have a look at the picture on the right. In that picture there is an inlet box, a UV lamp tray, and an outlet box. These form one continuous watertight vessel. Water enters through the inlet box and floods it, flows along the UV lamp tray to the outlet box, and at the outlet box end there's a weir wall which maintains a constant level in the UV lamp tray. Once water enters the outlet box, it exits. If you look at the photo on the left, the camera was placed inside the outlet box and pointed in the direction of the inlet box. You can see the submerged UV lamps in the water in the lamp tray, and you can see the weir wall in the foreground. For the pilot study, I placed a sump pump in the outlet box and flooded the outlet box, inlet box, and lamp tray with 168 liters of water. The discharge line from the sump pump was then routed back to the inlet box. In this way, I was able to continuously recirculate the inventory across the UV lamp tray during my test, which lasted 24 hours. Again, the water source I used was turbid, so I pre-treated with electrocoagulation to remove the solids. In this case, I used one of our larger industrial size EC units to do that. So for this study, I did an initial ammonia reading mid-morning and another one at the end of the same day, which is about 6 hours of recirculation time. Finally, I did a final reading at the next day at 24 hours. The graph shows that we clearly reduced the ammonia concentration. At this point, I was convinced that an investment in a large, high-power ultraviolet system for remote site deployment would be worthwhile. I felt I needed a bigger laboratory to play with. So I purchased unused surplus equipment from the oil and gas industry. I bought 2 identical UV water treatment units, each containerized in a 20-foot shipping container. They were originally designed for dropping onto an offshore platform and sterilizing seawater used for drilling and production operations, but they'd never actually been used due to the downturn in the industry in 2019. Each containerized unit has 2 UV reactors arranged in parallel. The piping is 12-inch diameter, and if you look at the picture to the right, you can see the inlet side on the very right side of that picture. Water flows along the pipe to the left and enters the bottom of both reactors. Each reactor has isolation valves, so you can run one and leave the other one shut down, or you can run both. Water floods the reactors up from the bottom and overflows out the top. The flow then recombines and exits the container to the left of that picture. So next I have a short video to show the actual field setup on site. I'm walking alongside the generator on my right now, and now we're going to swing around the back and have a look at the generator's control panel to give you an idea of power consumption. So we're running at 480 volts AC, 260 amps. So that's 130 amps per container. And now we're going to swing around the back of one of the containers now and enter through the reactor room And you can see the two UV reactors with their corresponding shields installed. Water again flows in through the bottom, floods the reactors and flows around the quartz thimbles and then exits through the top. You can also see some sample points here on the inlet and another one on back here on the outlet. And I'm showing the 4 isolation valves in blue. Next we'll have a walk down and have a look at one of the control panels. And we can see the dosage of 3915 millijoules per centimeter square being displayed, as well as a flow rate, in this case 37 cubic meters per hour. And I can scroll through the screens here, and I can also display an actual UV intensity, in this case 1.44 milliwatts per centimeter squared. And the other reactor has its own dedicated control panel, and it's displaying the same type of information. So we have a dosage, a flow, and I can scroll down again and get the intensity. And here is the actual controller for the flow meter. And now we're going to exit again. And next we have a couple of pictures to show what the inside of each reactor actually looks like. On the left, you can see the 12 lamps arranged around the reactor head. In the center, there's an electric motor which drives an automated wiper system. This activates on a timer and sweeps the quartz thimbles every 6 hours. In this way, the thimbles are kept clean and free from debris. The right picture shows what the reactor would look like if you were looking down the outlet from the top and inside the reactor. You can see the quartz thimbles are arranged perpendicular to the direction of flow, which in this case would be towards you and coming out of the picture. Next, we have a picture of an actual UV lamp on the top and its associated quartz thimble on the bottom. The quartz thimble looks like a big test tube. The outside of the quartz thimble is in contact with the water, while the UV lamp sits inside and stays dry. The lamp is never in contact with the water. These lamps run at about 900 degrees Celsius. The operating voltage is around 1400 volts, and the output power is 3500 watts each. A single lamp has 5 times more power than all of the industrial lamps I used in the small pilot study combined. In this next slide, I wanted to give you some context as to the relative UV intensity of the equipment I used for the various studies. Sunlight on a bright sunny day at noon gives a UV index of 10, and that works out to an intensity of 1/4 watt per square meter at sea level. A tanning bed is 80 times more intense than that at 20 watts per square meter. When you take into account the inside surface area of the PVC housing in my UV lamp study, the little 15-watt lamp actually gives you a UV intensity of 227 watts per square meter. That's an order of magnitude more intense than a tanning bed. In the small-scale pilot study, the intensity works out to 1,062 watts per square meter. So our small-scale industrial unit was just under 5 times more intense than the lab unit. Finally, the large UV system we use for the UV field study has a massive UV intensity of 62,000 watts per square meter. We have a very large amount of UV energy being released inside of a small reactor. So when you do the math, that's about 250,000 times more intense than sunlight at sea level inside of one of these reactors. Here we have a few images to show the setup for the field case study. On the left, you can see the 2 containers next to each other, and to their immediate right is the generator we use to power them. The settlement pond is actually not visible in this photo. Rather, it is down a hill and behind the containers. The top right picture actually shows the settlement pond. We set the UV container discharge point to be as far away as possible from the submersible pump that fed the containers. In this way, we felt that we were maximizing mixing and circulation in the pond. The image on the bottom is a simple flow diagram showing the arrangement. We circulated water from the pond through the two UV containers and back to the pond continuously for 24 hours a day over a 29-day period. For the field study, the water was already very clear, so there was no need for any pre-treatment. We did not need to use electrocoagulation on this water source. In the paper, I discussed something called a static reactor test. I did this test purely out of scientific interest. The underlying photochemistry involved with photooxidation of ammonia is well beyond the scope of my paper. But to suffice it to say, the reactions involve something called a hydroxyl radical, which is a very energetic, uncharged species created from water and ultraviolet light, and it has a very short half-life. Its presence is not easily detected in water with portable field equipment. However, I knew that if I was successfully generating hydroxyl radicals, then we should also see some hydrogen peroxide being generated. Hydrogen peroxide is relatively easy to detect with a handheld kit. So I flooded one reactor with field water and then shut off the UV lamps. I took a sample of the inlet water before starting, and then I isolated both valves to the reactor so that there was no flow through the reactor. I turned the reactor on for 180 seconds. The UV exposure time was short as the water in the reactor immediately began to heat up due to the no flow condition or static condition, and I didn't want the reactor to overheat and trip the high temperature shutdown limit. I then shut the reactor off and collected samples of the water that had been UV irradiated. I analyzed for ammonia content, peroxide content, and cyanide content before and after UV exposure. This graph clearly shows the production of hydrogen peroxide in the static test, which lines up with the reaction mechanisms reported in the literature. I was pretty happy with this result, as it was a clear validation of the underlying science. I also saw that the cyanide content had dropped dramatically, which was a promising sign that it would also be destroyed by our UV equipment. Finally, I noticed that the ammonia content actually increased in the static reactor test. This was expected though, as ammonia is a reaction product of the cyanide destruction. I initially expected the ammonia to increase due to the destruction of the cyanide. I would expect that the ammonia content would eventually drop after all the cyanide was consumed. However, I could not run the test much longer than 180 seconds due to overheating concerns, so a reduction of ammonia was not observed in this short-term static reactor test. Next, we have a timeline graph showing the total ammonia measured and the calculated unionized ammonia. The calculated unionized ammonia uses water temperature, pH, and the total ammonia measured as inputs. There is a clear downward trend in the total ammonia and the calculated unionized ammonia over the 29-day treatment period. I mentioned in the paper that the client was unable to pass their acute lethality test for rainbow trout in the months leading up to the treatment. Basically, the unionized ammonia exists in the water as a dissolved gas, the same as oxygen. The dissolved gas sticks to the fish's gills and hinders their ability to respire, and they suffocate. The client did twice weekly ALT testing over the 29-day period. During the last week of the treatment, the water started to pass the ALT tests, and the client was able to successfully and safely discharge all 9,000 cubic meters of water. This graph shows the cyanide content in the water over the 29-day UV treatment period. Again, it shows a clear downward trend. It is likely that the cyanide also contributed to the toxicity of the water, and we were clearly able to reduce it using the UV treatment. And finally, I'll summarize with a simple before and after graph for the field case study. Total ammonia dropped from 11.38 to 5.98 parts per million, a 47% reduction. Unionized ammonia dropped from 0.592 to 0.025 ppm, a 96% reduction. Finally, cyanide dropped from 0.53 to 0.06, which was an 89% reduction. Most importantly, the water was made less toxic and the client was able to successfully discharge their water after treatment. This concludes my presentation, and at this stage I would like to invite your questions.